Hello everyone, welcome to the Science Tuition Academy and to today's physics lesson, which is on current, charge, potential difference, and resistance. Today we're going to meet all of these very important concepts all in one lesson. Let's go for it and let's make a start. So first of all, we're going to start off with the definition of electric current, and we're going to make sure, and this is very important, that we actually understand this. So here goes. Electric current is a flow of electrical charge. An amount of electric charge is called a coulomb. The size of the electric current is the rate of flow of electric charge. What does that actually mean? So here in this diagram, we have a battery made up of two cells. And basically, there are charges called electrons which are flowing along the wire or conductor, and they're flowing to the components in the circuit, which may be lamps or maybe something else, and then they flow back to the cell or battery. These electrons are carrying electrical potential energy. So the electrons or charges are carrying energy, and this energy is given over to the lamp or the bulb or whatever component there is. So let's just go through that once more. Coming out of the battery and going along the conductor are little charges called electrons. They have a negative charge, as you probably know from chemistry, and they are carrying energy, and they go wee around the circuit, and then they go back to the battery to collect more energy. Now, electrical charge is measured in coulombs. More on that later. So basically an amount of charges or amount of electrons is called a coulomb. Now, the charges make up an electric current. So the more charges that are flowing in a second past a certain point, the higher the electric current. So the electric current is made up of electrons or charges that are flowing. And of course, we're going to build up on that even further. On the right, you've got another diagram, and this is just a model showing that the cell or battery is in fact Santa Claus, and he's giving little gifts or presents to his elves who are delivering these gifts, which are basically packages of energy. They're delivering that to the bulb, and they're coming back empty-handed. So you can see the electrons are going round and round the circuit, carrying energy from the cell or the battery. So this is a closed loop, which is also called a series circuit, which you've probably studied in lower school. And the current at any point in this circuit, okay, is the same as the current at any other point in the circuit, because the number of electrons or charges going past is at the same rate at the same time. Okay, so whether you measure the current here or here or here or here or here or here, the current will always be the same. So it can actually be measured at any point. Make sure you have written down the definition and any other points that you want to write down. Okay, so a current is a flow of electrical charge. Okay, the faster the flow of electrical charge, the higher the current. The slower the flow of electrical charge, the lower the current. Okay, now moving on. This is the inside of a wire or conductor, and you can see the electrons as they go past a certain point. Okay, electric current in a metal or conductor is the flow of charges or electrons from negative to positive. Now, the electrons are negative, so they actually come out of the negative terminal of the cell, and then they go around the circuit back to the positive terminal. Okay, I know some teachers will often say that current flows from positive to negative, but it is actually negative to positive. But that doesn't matter so much at GCSE. Now, let's pretend for a moment that these electrons were actually pupils or students in a school corridor. Okay, a teacher is standing at a certain point and he is or she is um, recording how many pupils pass that point each second. Okay, so you could have three pupils past that point in a second, that point in the corridor, or you could have 20 pupils past that point in a second. And this is very similar to what's happening with current and charge. Okay, the amount of charge that goes past a certain point, okay, in a second is called the electric current. Okay, so the number of coulombs of charge going past a certain point in the circuit in a second is called an amp of current. Okay, electric current is measured in amperes. We normally shorten that to amps, and the symbol, of course, is capital A. We use an ammeter to measure the current. That's what a typical ammeter looks like. And that, of course, is the symbol for ammeter, which you've met in the previous lesson. Moving on. So, because electric current is the same at any point in a circuit, it doesn't really matter where you put the ammeter. Okay, you can put the ammeter here. You can put it right next to the bulb. You can put it on the other side of the bulb. You can put it right next to the cell or battery. The ammeter can be added anywhere in that loop in what we call is a series circuit, and it will measure the current flow through the circuit. Okay. Now, lots of people find current, charge, potential difference, resistance, and so on very, very, very difficult. So I'm going to show you my pizza model. Okay, this is a nice way of explaining. If you don't understand these things, it's a nice way of explaining how electric current actually works. Okay, so we have here a pizza shop. Now, the pizza shop producing pizzas is like the cell or the battery. Over here, we have a lamp. A lamp is a little bit like a house. There's a party going on in the house, so lots of energy is needed. Where's the energy going to come from? It's going to come from pizzas from the pizza shop, okay, which is the cell or the battery. So the pizza shop is going to supply pizzas for energy, and the pizzas are carried by the moped drivers. Now, the moped drivers here carrying the pizza or energy are the actual charges or electrons. So these whiz around the circuit, these moped drivers whiz around the roads. They go from the pizza shop to the house, which of course is the lamp. In the same way, you have charges or electrons carrying energy from the battery, and they carry the energy around and they give it to the lamp. Okay, so the pizzas are the energy, and just as energy is supplied by the electrons to the lamp, in the same way, pizzas are supplied by the moped drivers from the pizza shop to the house. So the moped drivers are carrying pizzas to give energy to the house. In the same way, electrons are carrying energy to give to the lamp. Now, what happens once the pizzas have been delivered? The moped drivers go back. They go back empty-handed to the pizza shop in order to collect more pizza to deliver to more houses. In the same way, the electrons come back with less energy to the battery and they gain more energy, and then they go back around the lamp. So the electrons continue to flow around and round, and just as the moped drivers continue to flow on the roads and carrying the pizzas with them. Okay, now the difference between the energy at the start and the end of the circuit is called the potential difference. So if you measure the difference in energy um, on this side of the pizza shop, where the moped drivers are going out with the pizza, and the this side of the pizza shop, where they're coming back empty-handed, or if you look at the pizzas or energy being supplied to the lamp and the number of pizzas or energy coming back, that difference is called the potential difference. So it's really the difference in the energy at the start and end of the circuit. So this is a really, really nice model to explain how the current actually works. So the current is the flow of charges. The charges are the mopeds. So the current is how many moped drivers are actually leaving the pizza shop with pizzas. Okay. The lamp is like a house with a party going on. The pizza shop is the battery. The moped drivers are the charges, okay, or electrons, and the pizza is the energy being supplied to the lamp from the battery. So hopefully that was a really, really nice pizza model, which explains electric current. If you want to, of course, write that down to help you remember, then that will be very helpful for you indeed. Okay, pause if you need to, otherwise let's move on and go even further. So flow of charge, okay, or charge flow, is current times time, okay? Now, if you rearrange that, current is charge flow divided by time. So the number of charges or amount of charge that's flowing in a second past a point in the circuit. Just like we said, the teacher in the corridor counting pupils going past in a second. So you can actually measure, okay, the charge flow in 1 second, 2 seconds, 3 seconds, and you can use that to work out the current. So charge flow is measured in coulombs, as we said, and the symbol for charge flow is Q. The unit is coulombs, which is capital C, not to be confused with current, by the way. That's in amps. So the symbol is, the unit is capital C for coulombs, for charge flow. So C for charge flow, C for coulombs. And the symbol for charge flow is a Q. Charge flow equals current in amps, and the symbol we use is I, times time in seconds, and the symbol we use for time is, of course, T. Now, if we were to put all of that into a triangle, you can see that, and you know how to use the triangle because obviously we've used that quite a lot recently. So charge flow Q is I times T. If you want to find out I, the current, you cover up current or I with your finger, and you get Q divided by T. Okay, charge flow divided by time. Coulombs divided by seconds. Please pause the video and write this down, and then, of course, we'll move on. Okay, so what we're going to do is we're going to do some simple worked examples. And the first one, calculate the charge that flows in a wire, which has a current of 1.2 amps for 30 seconds. Now, what we're going to do, first of all, is we are going to annotate, calculate the charge. That means you are after Q. That flows in a wire which has a current of 1.2 amps, that is I, for 30 seconds, which is T. Okay, now this is what you're after, Q. Now, when you rearrange the equation and or the formula triangle, you get Q equals I times T. So electric charge is current times time. Q equals I times T. So it looks a bit like quit. Okay, that can be a nice, quick way of remembering that. Now you've got I, 1.2 amps, times T, 30 seconds. 1.2 multiplied by 30 gives you electric charge of 36 coulombs. Okay, nice and easy. You're working out charge. Charge is Q, and it's measured in coulombs. Okay, let's do another worked example, which obviously you can do, okay, in order to build your confidence. And this is the second one. A charge of 16 coulombs passes a light bulb in 5 seconds. Calculate current through the bulb. So this time you're after current or I. Off you go. And then we'll go through the answer. Give you 10 seconds. Okay, hopefully you've worked that out by now. And of course, if you need extra time, of course, just pause the video. That's absolutely fine. First of all, I'm going to annotate on this screen. So we have a charge of 16 coulombs. That is, of course, Q. And then we have 5 seconds. That is time. And you are going to calculate the current, which, of course, is I. So you are after I, again, as we have said, cover up I, and you are left with Q divided by T. So electric charge is current times time. Current, when you rearrange it, is Q divided by T. That's charge flow divided by time. That is, of course, 16.0 divided by 5, and that gives you a nice current of 3.2 amps. Hopefully you found that nice and easy. Okay, so just make sure you've got that down. Of course, do pause the video if you want to. Okay, now let's move on to the following. So we've got 3 questions. Okay, we've got easy, we've got hard, and we've got challenge. Okay, so pause the video and work through these, and then we will unpause and go through the answers. So please pause the video now. Okay, unpausing, I'm just going to go through the answers. So the first one, which is particularly easy, you're working out the electric charge, which is Q, when the current in a bulb is 0.2 amps for 60 seconds. As you can see from the triangle above, Q equals I times T equals 0.2 amps times 60 seconds equals 12 coulombs. Okay, now notice I didn't annotate the question, but I'm more than happy to do that. So you are working out Q, and it gives you the current, which is I, and it gives you the time, which of course is T, and is 60 seconds. For the second one, calculate the current in an electrical device. So they're after I, and they give you Q, and they also give you T. So please pay attention to what information they actually give you in the question, and please annotate your exam questions like this. Okay, you can write around them, you can annotate them in whatever way you want. For the challenge question, we might as well annotate that one as well. A wire carries a current of 6 amps, that is I, current. Symbol for current is I. For 5 minutes, that's time. And you've got to calculate the charge, which of course is Q, and charge is measured in coulombs. Now, this one, of course, is a tricky one because 5 minutes, well, we don't deal in minutes, we deal in seconds. So you have to do 5 times 60 in order to find the number of seconds. So coming up to the answers now. So we have the following. So we have current is Q divided by T. That's 80 divided by 16, which gives you 5 amps. And for the challenge question, calculate the charge. Q equals I times T. I, of course, is 6 amps. However, we've got 5 minutes. We have to do 5 times 60 because there are 60 seconds in a minute, and that gives you 1,800 coulombs. Please make sure you understand all of these three typical questions and you have got them right, or you know exactly how to calculate them. Okay, let's move on. And let's now have a look at a very, very difficult concept of potential difference. Okay, P for potential difference, P for pizzas, if we go back to our old model. Now, for electric charge to flow through a closed circuit, the circuit must include a source of energy or a source of potential difference. And this source is a cell or battery of cells. On the left, you can see what happens in a conductor or wire when no potential difference is applied. You can see that the electrons, if they are moving at all, the free electrons, then obviously it's a sort of random movement. However, when you apply a potential difference from a cell or battery, you can see that the electrons or charges are all flowing in a current, as you can see in the diagram there, from the negative terminal of the battery to the positive terminal. So what is potential difference? Potential difference is a measure of the difference in electrical potential energy between 2 points in a circuit. It is the energy transferred to each coulomb of charge. So the battery or cell is providing energy to each coulomb of charge and then to the bulb. As we are talking about energy transfer, as we've already seen in the lesson on work done, we can also say the work done by the bulb. So whether you talk about the energy transfer to each coulomb of charge, or you talk about the work done by the bulb or lamp, it's the same and it's in joules. So the potential difference is the energy transferred to the bulb or the work done on it by each coulomb of charge that passes through it. It's measured in volts using a voltmeter. And of course, the unit of potential difference is the symbol is V for volts. 1 volt is 1 joule of energy per charge, or 1 joule per coulomb. So voltage, which is another word for potential difference, relates to the energy given by the battery to each charge. And just as we said, the pizza's going to the house, delivered by the moped driver, and the number of pizzas being brought back from the house to the pizza shop, which of course is 0. That difference in the number of pizzas is a bit like the potential difference. It's the difference in the energy that the charges actually have. So if 1 volt is 1 joule per coulomb, so a 6 volt battery will give 6 joules of energy to each coulomb of charge. What about a 12 volt battery? How much energy will that give to each coulomb of charge? It will give 12 volts. Okay, so you can see potential difference at the top. You can see potential difference is energy transferred divided by charge or number of charges. Okay, so V equals E divided by Q. All right, now moving on. What is potential difference? So It's the energy transferred per unit charge as charge moves between 2 points in a circuit. It's measured in volts using a voltmeter. The voltmeter, as you can see in this diagram here, is connected in parallel. It's connected across a component, so you can measure the difference in the potential difference or difference in energy transferred by the charges here and here, before the lamp and after the lamp. Okay, so when we measure with a voltmeter, we say measuring across a component like a bulb, so we get the difference between the 2 points in electrical potential or electrical potential energy. The voltmeter is always connected across the component, so in parallel, which means that the voltmeter has its own loop and it has two wires sticking out of it, which connect to the rest of the circuit. Moving on now, if you do need to go back to have a look at potential difference and write any notes, of course, please do rewind. We're coming on to the last bit, what is resistance? So we've looked at charges or charge, we've looked at current, we've looked at potential difference, which is to do with energy transferred, and we are now looking at resistance to the flow of current. So let's have a look. This is an electrical conductor, which is usually in a circuit a copper wire, okay, made up of copper atoms. And this copper wire will allow an electric current to pass through, okay? And of course, the electric current will be made of electrons or charges. Now, metals are really good electrical conductors because, of course, they have free electrons and they have metal atoms, or you can call them ions. It's these free electrons that are actually flowing through the conductor, making up the electric current or flow of charge. The free electrons are pushed by the potential difference, and the metal atoms do not move and they only vibrate in fixed positions. It's only the electrons that move, okay, in the flow of charge because they're given energy by the cell or by the battery. So that's the potential difference. Okay, please pause the video and write these notes down for your notes so you've got them step by step. Otherwise, let's move on. Now, when the free electrons move, they collide with the metal ions, which resist the movement of the free electrons. So you can see in this model that resistance is basically resistance to the flow of free electrons through the copper wire. Now, another way of saying it is, if we go back to our pizza delivery model, if there is something like a road blockage which is resisting the flow of the mopeds carrying the pizzas, in which case, of course, the pizza is going to be late to the house, or there's not going to be much pizza delivered in a certain time. Now, in the same way, what you've got is you've got an example going back to the school corridor where you've got some sort of obstruction in the corridor, which means that the movement of pupils is slowed down along the corridor. Okay, so this is resistance to the flow of electrons. Okay, they're colliding with the metal ions, which inevitably does happen. Now, the metal ions or atoms begin to vibrate even more, and the free electrons are bumping into them. And when they're vibrating, the atoms take up even more space, which makes it harder for the free electrons to pass, which further increases the resistance. And that will, of course, increase the temperature of the wire because of the increased vibrations of the metal atoms. This is why, with resistance, you can find that wires get hot and that increases the resistance further. So please pause and write down any notes you want to, and let's move on. So you can see here in a bulb or lamp, you can see that the resistance is so high that the filament in the bulb, we've met the tungsten filament before, begins to glow white hot, and it actually releases light energy. And that's because of the high resistance. The electrons are going through a very, very, very fine filament. You've got the electrons, you've got the atoms, which are vibrating. So you've got high resistance that causes a high temperature and causes that white glow in the filament bulb. Okay, now resistance can be good and it can be bad. In this case, it's good because, of course, you're getting a white light or yellow light. So this is the basis on which filament bulbs work. But it can also be bad because, of course, a lot of energy is dissipated as thermal energy or heat energy. So, in other words, these filament bulbs are not very efficient because a lot of the energy is transferred to thermal energy rather than light energy. Okay, so I have a diagram there, and two of the labels are obviously covered up, and we've got some blue particles. So just have a think for a moment. Number one, what do the blue particles represent? Number two, what is pushing the blue particles above? And what is the flow of the blue particles called? So we're bringing it all together, all of the concepts that we've actually studied. Number three, suggest what the hand represents in the circuit above. What causes the hand in the circuit in our model? Okay, so that is the copper wire. We've got blue particles. Just pause the video and have a think about the answers to these questions before I go through them. Okay, let's go. So we have the flow of charges, the blue particles, or which are electrons. So that flow is called a current. And we have resistance, of course, which is trying to slow the flow of charges or current down. Okay, so the blue particles are the free electrons in the circuit. The free electrons are pushed by the potential difference or the voltage. The flow of the blue particles, which are the free electrons, is called current. And the hand in the circuit represents the resistance, which is caused by the free electrons colliding with the fixed metal ions. So we've discussed all of that. There's nothing new there. Okay, but the resistance is trying to slow down the flow of the electrons, and that's because they are colliding with the fixed metal ions. Okay, please pause and write down any notes that you think you wish to write down. Otherwise, we will move on. Okay, so this is another equation. So we're bringing it all together today, and you can see it's a very, very, very important lesson. Okay, because we're looking at charge, current, potential difference, and resistance. Okay, now what I want to do is look at the relationship between potential difference or voltage with current and resistance. So we have this equation or formula, potential difference in volts equals current in amps times resistance in ohms. So we say V equals I times R. So a few questions for you to dwell on before I go through them. What two factors does potential difference depend on? Draw a formula triangle for V equals I times R. Where would V be? Where would I be? Where would R be in the triangle? Rearrange the formula above to calculate resistance. Remember, you don't have to use the triangle. That is just one method in order to, help people rearrange, but it's better to use your math skills really. And suggest how an increase in resistance affects the current if the potential difference stays the same? Okay, have a think. And please pause the video if you do need any extra time. And otherwise I will move on. So here we go. So if you want to draw the formula triangle, here it is. So V goes at the top, I times R at the bottom. So if you cover up the V, you will be left with I times R. I is V divided by R, and R, resistance, is potential difference divided by current. So it did ask you to calculate the resistance. It's V divided by I. Okay. How would an increase in resistance affect the current if the potential difference stays constant? So both using the formula and logically, if you get an increase in resistance, then of course the current will decrease. Okay, so what we're essentially saying is that if this stays the same, and if you get an increase in resistance, then you will inevitably get a decrease in current. Okay, so hopefully that makes sense. Please make sure you get down anything that you need to get down in terms of the formula triangle. And let's move on and let's do a worked example. Let's see if you can do this one yourself. Calculate the potential difference V when a current of 2 amps flows through a resistor of 5 ohms. Please do that now. Off you go. Okay, pause the video if you need any more time. And we're working out V, the potential difference. V equals I times R. Simply 2 times 5 gives you 10 volts. Okay, so hopefully you got that correct. Let's do some more. Okay, so I want you to read through all these, annotate them yourself. Okay, you should be quite good at that. Annotate where is V, where is I, where is R, which one is the one you're trying to work out. Rearrange the formula using the triangle. So pause now and off you go. Okay, so unpausing, let's go through. The first one is asking you to work out V, simple as 20 times 0.5 amps, which is 10 volts. Second one, calculate the current. I is V divided by R. 12 divided by 100 is 0.12 amps. And the last one, now this is a tricky one, and the reason it's a tricky one, I will now annotate it now that you've had a go, is because a milliamp is a thousandth of an amp. So 100 milliamps is 100 divided by 1000, which of course gives you 0.1 amp. So when you actually work it out, you can either do 100 divided by 1000 in brackets, or you can do 0.1 amps. And so resistance is V, which is 6 volts, divided by 0.1 gives you 60 ohms. Okay, hopefully you got that correct. If you have, absolutely fantastic. Not only have you learned all of these 4 difficult concepts, which are one of the most fundamentally misunderstood parts of physics, and you've been able to do some of the relevant questions, which we will only build on further later on in order to get those top grades. Okay. How can you measure the resistance of a bulb? Okay, first of all, there are some questions there. I'm just going to remove the text or the writing. What is the formula to calculate resistance? What 2 pieces of equipment do you think you need to measure the data needed to calculate resistance? And draw a circuit diagram to show how you would connect the equipment to the circuit above. Okay, just have a think for a moment. What equipment would you use to calculate the resistance? Well, to calculate the resistance, you would need to know the potential difference measured in volts. That could only be a voltmeter. And of course, you need to know the current measured in amps. That could only be an ammeter. So the way in which they are connected is as follows. Reminder that ammeter in the main loop of the circuit, okay, and then you've got your voltmeter in parallel to the lamp or the bulb, okay, connected in this way on its own loop. So this is how you measure the resistance of a bulb. Okay, so three questions. Which apparatus measures current? Which is connected in series? Which is connected in parallel? We've already answered those questions. And calculate the resistance of the lamp. So to calculate the resistance of the lamp, you need the voltage or potential difference. You need current. R equals V divided by I. 6 divided by 1.5 gives you 4 ohms. That is the resistance of the lamp. Do copy out the circuit and the works example if needed. If you understand it fully, that is absolutely fine. We'll only build on it and it will get harder and harder in subsequent lessons. Okay, so last bits. What are the formula triangles above linked by? Can you see they've got one thing in common? Okay, this is where we're going to use two different triangles. We've done this previously with kinetic energy and gravitational potential energy. And of course, the common feature or factor is, of course, current, which is I, and it's found in both formula triangles. Calculate the resistance when the potential difference is 2 volts and the current is 2 amps. Now that's the triangle on the right. So R equals 2 divided by 2, which gives you a resistance of 1 amp. Calculate the resistance of a bulb. This is a bit harder now, with 2 volts potential difference and a charge of 200 coulombs for 50 seconds. Oh dear, it's asking you to work out the resistance. Okay, and you've got a 2 volt potential difference and it doesn't give you the current. So first of all, you have to work out the current using I equals Q divided by T. That's 200 coulombs divided by 50 seconds. Once you've worked out I, of course, you can then put it into here and use it to work out the resistance. And your answer will be as follows. So I equals Q divided by T, 200 divided by 50 gives you 4 amps. You then do R equals V divided by I, 2 divided by 4 equals 0.5 ohms. Please do copy out the triangles. Please do copy out the worked example so you know how you can use one equation or formula in order to work out something in another formula triangle. Okay. Right, quick true or false quiz. And here goes. There are 6 statements on the screen. Can you write numbers 1 to 6 in your book and write down whether they are true or false? Go. Okay, pause the video in order to continue if you need any more time. And I'm going to go through the answers now. So number 1, potential difference is measured in amps. That is, of course, false. Potential difference is measured in volts. Always think about how you can actually correct the statement. Number 2, current is the rate of flow of electric charge. True, it is. You can go back to your notes and see that that is actually the case. Number three, cells and batteries are used to make electrons. That is patently false because they don't make electrons. The electrons are there in the conductors. Number four, potential difference is also called voltage. That is indeed true. Number five, current is measured in volts. False, it is measured in amps. Number six, potential difference is the difference in electrical potential energy between 2 points is absolutely true. Okay, so hopefully you've done well on that and you've got a very good understanding of charge, current, potential difference, and resistance. And please do go back over the lesson just before an exam if there's anything you need to look at over again. Other than that, thank you very much. Hope you enjoyed the lesson and hope you've really built a good understanding. Please do leave a comment, okay? And please do visit our website, sciencetuitionacademy.com, and our Instagram page for further information. Thank you. Take care and bye.